So hello everyone, and thank you for joining us. This is the fifth lecture of the second edition of the Current Topics in Heritage Science lecture series that is organized within the Hyperion HS Academy and the European Research Infrastructure for Heritage Science. My name is Tjaša Rijavec, and I am a researcher at the Heritage Science Laboratory at the University of Ljubljana. I will be moderating today's lecture given by Bernhard Blümich, titled Portable NMR Structural Diagnostics in Heritage Science. The recording of the lecture will be available on the E-RIHS YouTube channel, and at the end of the lecture, you will also receive a survey asking for your feedback, and if you want to receive the attendance certificate, please let us know. You can ask the Q&A function to ask questions that will be answered by the speaker at the end of the lecture. But if you experience any technical difficulties, do let us know through the chat. So to introduce our speaker today is Bernhard Blümich, whose work aims to understand the macroscopic properties of polymer and porous materials that include tangible cultural heritage by using NMR on a microscopic and on a molecular basis. He was the chair of the macromolecular chemistry at RWTH Aachen University and is a co-founder and director of Magritte Company, which is a manufacturer of tabletop NMR spectrometers and the famous NMR mouse. He developed and applied NMR methods for NMR spectroscopy of liquids and solids, NMR imaging of heterogeneous materials and fluid transport, and NMR relaxation and diffusion techniques. His recent work is focusing on compact NMR instruments, that is for non-destructive materials testing, and on diffusion under confinement. He has co-authored many books on NMR imaging, such as NMR imaging of materials, compact NMR, and essential NMR. So thank you for joining us today and introducing us to the topic of portable NMR in heritage science.
Well, thank you for the introduction. It's a pleasure to thank you for inviting me to present the work we have been doing and the technique. I always found it exciting and really rewarding to work on cultural heritage. Let me share my screen and go to the first page. Okay, now you see it, right?
Yes.
Okay, so the title has been announced, and let me come straight to the first page. NMR, the way I present it here, is a technique that allows you to analyze the stratigraphy of materials and characterize the material properties of these different layers that one observes. And therefore, I put it into the context of other techniques that are used in cultural heritage for measuring and characterizing stratigraphy. There was a lecture by Piotr Targowski. It was the first one in this series a couple of weeks ago, on optical coherence tomography, and there is also terahertz spectroscopy that does similar things. The resolution and depth range of all the techniques, which you see in blue on that slide, is different, but something like 3 to 10 micrometers seems to be the limit of the smallest structures one can resolve. But the frequency range, all of them work with electromagnetic waves, but the frequency range is vastly different. So if we talk about terahertz spectroscopy, then we are at something like 10 to the 12 hertz of an electromagnetic wave. Optical coherence tomography uses visual light roughly, but nuclear magnetic resonance, the way I show it here, uses the magnetic properties of the electromagnetic wave in a frequency range of roughly 10 to 20 megahertz. So this is shortwave radio, basically. Now, let's introduce what nuclear magnetic resonance means. So we have nuclei, we have magnets, and we have resonance. Nuclei, you know the structure of an atom. That's at the core of an atom. The electrons circle around it. We need a magnet where we put the object in that has these atoms and nuclei. So basically, that's matter. And then we probe resonance. And the resonance are in the range in NMR with instruments today of roughly 1 megahertz to 1.2 gigahertz. And I put a radio frequency tower here of my hometown in Berlin just to illustrate what we are dealing with. You can define NMR as a physical resonance phenomenon utilized to investigate molecular properties of matter by irradiating atomic nuclei in magnetic fields with radio waves. There are three manifestations of NMR in science today. And the most famous one that's probably known to everybody is NMR imaging, you know, from the clinics. I don't have a picture of a clinical tomograph. I have pictures of compact tabletop instruments that can be moved to different places over here. And this is sort of a development that was largely pursued in the group when I was still active in research. And here is a tomograph that is moved to some other research facility. The signal one sees in NMR imaging looks like that when you have an hexagonal array of a repetitive pattern. This is reminiscent of the scattering diagram you see in X-ray scattering from a hexagonal lattice. Except there you can't do a Fourier transformation, get the image, but in NMR we can because we have a phase-sensitive method. So we have the phase of the NMR signal, which you don't get in scattering experiments. You only get the magnitude of the signal. Now, that's imaging. Now, the other important and famous technique is spectroscopy used in chemical laboratories. People have these gigantic magnets, and they put a very teeny tiny sample in the center, and then they measure an impulse response. They have their own language. They call it free induction decay, and they do a Fourier transformation of that signal as it decays with all these oscillations and get a spectrum. And from that spectrum, they can read off the chemical structure of the molecule. It's a big thing. All the chemists know NMR spectroscopy. All the medical doctors know MRI. And what we are doing is we measure relaxometry. So we basically look at the same signal as the green one shown here, but we only look at its envelope, how it decays. And the reason why we do that is because we can measure that much easier. It's much simpler and much more robust and smaller instrumentation. And that is a signal. It relaxes from its maximum to 0. And then we can decompose it by fitting, let's say, many exponential functions that decay differently fast. And that distribution of their amplitudes is called a relaxation time spectrum. You see that here. Or is the population as a function of the different relaxation times. And this is what we analyze in the cultural heritage community. There is a transformation that where you can transform the red measured signal into the red distribution of relaxation times. That's the inverse Laplace transform. That's not quite mathematically correct. It's basically a solution of a Fredholm integral. That's where I put these two scientists here. But this is what we are dealing with. And that's good for materials testing, to look at physical properties of matter. Now, here's the sort of very short primer to NMR. We have a frequency, that's the radio frequency, let's say 20 megahertz in our case. We have a magnetic field, and the frequency is proportional to the field. Now, if we want to measure an NMR spectrum where the sample sits inside this huge magnet or a small tabletop magnet, then the field has to be homogeneous across the sample tube where the sample is contained. That's usually 5 millimeters. The homogeneity is 10 to the minus 8. I will show you in a minute what that means. And if we use the materials testing application with our instrument, we dubbed it NMR mouse for Mobile Universal Surface Explorer. Always have to cute name to sell it somehow. Then the magnetic field from a permanent magnet shown here on the right decays as you go away from that magnet. And that's an obvious thing. And that means, given the relationship on the left, that the frequency is proportional to field, it means you have high frequencies where you measure the NMR signal close to the magnet and low frequencies further away. It's sort of like a piano keyboard where you have the high tones on the right and the low notes on the left. And while in spectroscopy, all the instruments have to be exactly at the same pitch. And how exactly, that's the amazing thing. So in spectroscopy, you need a homogeneity of 10 to the -8. Well, that's sort of a number, and it's hard to imagine what it means. But it means that if you build a road that's 100 kilometers long, you want to have a variation in height of less than 1 millimeter across these 100 kilometers. And this is why it took so long to build such instruments, make them in compact, small form instead of these huge magnets. Now, all these restrictions don't apply when we use what we say the NMR mouse. This is that black box over here. It sits on a lift, which goes up and down. I'll show you why in a second. The object sits on top. And then one measures not simply an impulse response in the spectroscopy, but uses many pulses that create echoes. These are these green signals that pop up again and again and again between the pulses that we apply. And the envelope of these is a signal that we measure. And it's a very interesting phenomenon. It was discovered in NMR. It's related to time reversal. And that echo is, the spectroscopic echo is different from the physical echo. So spectroscopic echo means you shout hello into the mountain and you get ole back, right? And the next echo would be hello again. And then will be hello, ole, hello, ole. So well, it's backwards and forward. And these are some peculiarities that are just fun and have to do with, can we reverse the time scale and all this stuff, very philosophical. But here you see a signal as it's sort of being accumulated. This is the actual measured signal. There are two signals, real and imaginary part, because we have a phase-sensitive signal. But that essentially is what we transform. So you accumulate something like 1,000 signals, or here we accumulate 200. And that takes a lot of time. And so it's a very slow method. And the final signal after accumulation looks like that. See, it's quite noisy. And that noise then has to be, by mathematical procedures related to the inverse Laplace transformation, sort of filtering and regularization, is transformed into the distribution of relaxation times. And if we take the integral of that distribution and plot it as a function of depth, we get a depth profile. Now, what does it actually mean? Here is the mouse. This is a wall in Ostia Antica. And it's a wall with a fresco. And you see it from the side. If you would look into the wall, you would see the stratigraphy of the mortar layers on which the fresco is painted. So that's this. And the NMR frequency is set in such a way that the signal comes from 25 millimeters away from the surface of the sensor from a very flat sensitive slice. That's the construction of the device. Now, the mouse sits on a sled, on a translation stage, which can be driven electronically back and forth. So you move that slice back and forth through the wall. And until the sensor touches the wall, you can't go any deeper. So that gives you the maximum depth range. And then from that signal that you measure at each position, you get that depth profile. And this is a depth profile through a fresco. And you see all kinds of structure in there. And this is what we are interested in. It takes about 1 hour to measure such a depth profile, so it's not a fast method, but it gives you some interesting information. What we actually measure is we measure the signal amplitude, measures the amount of water in that sensitive slice, in that red little bar that you've seen in front of the sensor. If you normalize it to a signal from pure water, you get volumetric moisture content. And here you see volumetric moisture content in the Chapel of St. Mary, that's this one here, of the Royal Abbey of Charlies, that's this one here, which has been dismantled to pay the debt of the monks. And it has some painted wall, which was repainted because there were water issues. You see the water issues right here on that slide. And we measured at 8 different spots on this wall. You see the position of one of them. There is the NMR mouse, sits on a scaffold. There is the translation stage, which moves it back and forth. And we measure step by step these depth profiles. Here is one. Let's point out this one. And you see it goes over a depth range of 20 millimeters. And it goes from 0 moisture content all the way to 6% or 5% moisture content. Now, how does that compare to other methods? First of all, it measures moisture directly because it measures the hydrogen signal. So there's no indirect measurements. If you take electrical measurements, they always are impacted by the conductivity. Now, pure water is non-conducting. So you need ions in there. So you measure the dirt when you do an electrical measurement. And so there were other people in that measurement campaign that measured evanescent field dielectrometry. That's a measurement with microwaves that penetrate the wall, and they penetrate them also about 2 centimeters, 20 millimeters. And they do a weighted averaging over the moisture content in these 20 millimeters. So that's a gray shaded region here. And what we have done is we've taken our profiles and sort of integrate another weighted integration, which is not sort of guessing, how that weight could be. So to match more or less the means which we got by electric field dielectrometry, difficult word for me. And you find that there's reasonably well agreement. Of course, the electrical measurements, takes a minute or something. It's very fast. But you don't get these gradients. But the gradient relates to the moisture flux according to Fick's second law. And moisture flux means the water is sucked up somewhere from the bottom or from the top, wherever it comes from. And the gradient tells you how fast it goes out into the open air. And that's a crucial quantity one should measure, not the moisture content. The flux is important for carrying the salt to the surface where it crystallizes and destroys the painting. That's something that hasn't quite entered the heads yet of the conservators and restorers, that is not moisture content, it's moisture flux. But it's difficult to measure. And so that's why people measure moisture content and not moisture flux. So what we can measure with the NMR mouse, we can measure which fresco fragments belong together if we have fragments, which was the status of the building owner, depending on the fine structure of the depth profile, where the different frescoes prepared by the same workshop is the same technique used in different rooms of the building. How was the fresco prepared for painting? Does the wall painting cover an older one? These are some of the questions that can be answered. Now, the other thing is we need a signal, the signal has to come from hydrogen atoms. And the hydrogen comes from residual water in the wall, or we even spray the wall with distilled water. That's slightly invasive, but can be done in very often. But you have an issue when the wall has been treated with a hydrophobic agent so that you don't get the water into the wall. But you can measure wax that has been used to conserve, let's say, a fresco. And and it takes about 1 hour to measure. Now, let me give you some example. We have been in Ostia Antica, and that's the port of ancient Rome. And the river Tiber in antiquity is a dark blue line. And then the sediments changed its course to the light blue course. And this is the old city of the excavated part of Ostia Antica. Most of it is excavated, and the places are marked where we measured. And here's some depth profiles. There's a depth profile of a fragment which we measured, where a newer section of a fresco is covering an older section. And we wanted to see if we find the signature. And so we measured these distributions of relaxation times, that blue shaded map here. And then we took the signal amplitude, that is the integral along that line in each direction, and get the depth profile. And you see there's several layers of mortar which one can identify. Here's a side view overlaid with the NMR signal. And the major structures you can identify even from the side view. There's certainly different color here and a different color here. And this is the line where the new fresco on the left covers the old fresco. And that shows up in that distribution of relaxation times that there's hardly any signal, and there's a little dip coming up here. Now, we wanted to test that on buildings. And so we had 2 cases. One was the house of the bath supervisor, Butikosos, and the other was the garden house complex. And in both cases, we could see there were actually a newer layer mortar structure was covering an older one. And we do see these distributions of relaxation times, and we see that dip and that sort of interruption of these 2 distributions of relaxation time that we see here. What you see here is an overall change. of the signal, which saw there seems to be a trend in it as you go to larger depths, 20 millimeters in this case. This has to do with the fact that we spray the wall, the water takes time to go into it, 20 minutes something, until you get measurement signal. But of course, you still have more signal at the top than at deeper inside the wall. And a similar signature was discovered in the Garden House complex, because we noticed actually then that there's also 2 layers of mortar bases. Basically, the whole mortar layer structure was applied twice, and there's no clue why that has been done. Well, we found that it has been done, and it waits for an answer of the historians to tell us why that possibly could have happened. Now, here's an interesting study we did recently in 2022 in Ostia Antica. And that involves the measurement of, again, different fresco profiles in different rooms. And the most interesting one is in the house of the charioteers. And there is, first of all, a corridor that has 2 frescoes with paintings of charioteers. You see them here, A and B. And there's also another room, room 9, that is on the right, shown here, where a newer fresco is covering an older one. Now, we measure depth profiles in 2 spots, A and B, in the corridor where these paintings are, and 2 profiles, the new one and the old one, in room 9. And what we found to our surprise, that these profiles are very similar. And this is strange, because obviously in room 9, the old and the new one are done at different times. So they must have been done, you know, with different techniques at different times, because the new one is covering the old one. Now, we found these different techniques on one wall, which is painted here. And this is a mystery that we're trying to solve at the moment. It is exciting insofar as if you go into you know, the literature and read what the dating of this painting is, then the dates can vary by more than 100 years. And there's obviously different criteria used on pigments, but none so far on depth profiles that refers to the dating. And one should really consider both to get a clear answer. We measured another room, another complex here, and that's the house of the painted ceiling. You maybe see in the background, you know, all these beautiful paintings. And we couldn't measure them because they had been detached and remounted. And that means all the mortar layer structure got lost. So we measured in different places. The room with the painted ceiling is room 1. And we measured in all these spots that are labeled A, B, C, D, E, F. And these are the depth profiles we measured. And there's similar depth profiles, A, D, and E. They are A, D, and E over here. And there is has been a wall right here. That's a thin line there. And that wall is gone. You see that outline of the rest of where the wall was right here. We measured right and left of the former wall and found that the depth profiles C and D are very different. So that means the wall over here, this is another corridor or entrance hallway, has been done at a much later time. It is probably done in a water, in a hydrophobic type of cement, because the flooding must have increased at that point in time. What is interesting in this whole thing, we could measure in one room, that's where we measured profile F over here, of a fresco that has been reattached to the wall, while the other ones all have been taken down and only the paint layer preserved. And we were interested in that because that could tell us what would the layer structure have been like that has gotten lost during the detachment. And we find that F is the signature over here, is this signature. And that's probably the signature that was used in room 1 where all the paintings have been taken off. Now, what happens when you take off a painting, detach a painting? This is a view from the top, very odd perspective to see. But you see the fresco here, you see a gap behind the wall that's there for ventilation to keep it dry. And it's mounted on a steel grid. Now, steel is a no-no for the NMR mouse because it's a very strong magnet, and you have to make sure it doesn't touch the painting. So that's a difficult measurement to do. But the depth profiles we measured at this detached fresco, they're worthless. You know, it just shows you see nothing because all the layer structure is lost. It's gone. And I can't move that. Oh yeah, this is a 10 millimeter range here that you look at. And there's another case. I'm losing time, so I would probably skip that. This is the house of the eagle. Again, inside, beautiful paintings, all of them detached. We can't measure them. But outside was one section that was still attached to the wall. Again, a very sophisticated depth profile. And that depth profile suggests that probably the paintings inside that room were of similar quality. All right. Now here's a different object that we measured. That's the Macintosh library in Glasgow. It burned down in 2014, was reconstructed, and it burned down in 2018. So that's a disastrous event. This is what it looked like before the first fire. This is what it looked like after the first fire. And people wanted to know if the sandstone structure at these windows here, how big is the damage with the sandstone? And we were called in actually in one of these MOLAB activities. I don't know if they still exist. And people wanted us to do NMR measurements with the NMR mouse. And so we measured in all these spots. Unfortunately, very bad picture, but a very bad resolution. But you see where the spots are. They go up to roughly 9 meters in height. And so we had to climb on that scaffold, and you mount the mouse, and you have to make sure it doesn't fluctuate, you know, by a tenth of a millimeter, because that's sort of the resolution that we get. And we measured the NMR relaxation times, a slightly different measurement. And these NMR relaxation times, then we did a similar measurement. The relaxation times are plotted here on the horizontal scale. And then we got sandstone samples which had been baked at certain temperatures, and we measured the relaxation times there. And this is how we could assign the temperature to the relaxation times. And we knew where we measured at what height, so we could determine the temperature of the fire at the height, at the different heights within the room. So we go from 350 degrees at roughly at the bottom C up to 900 degrees C up here, which is an amazing result because it's a pretty crude measurement. But it has to do with the changes of the chemical changes of the pore structure as a result of the fire and the associated wetting properties of the water with which we sprayed the wall before measurement. Now I'm coming to violins. I still have a few minutes, not too many. Very exciting study, again, a MOLAB study. We studied in two places. We studied in the Ashmolean Museum in Oxford, and we studied violins in Cremona. Now, in the Ashmolean Museum, they got a collection, their violins have been collected very early on, and they have hardly been played because the philosophy was, if you don't play them, they stay as good and don't deteriorate. Now, the question you may ask is, how good is a violin when you don't play it and it's very valuable? You can't enjoy it other than be sure you have a lot of money in the safe. So the pure enjoyment of having money in the safe is basically the enjoyment of the museums of the violins in Oxford, and of course the craftsmanship of making them. Now, Cremona didn't have a single violin left. In the 60s, they bought violins from all over the world, and they have been played. They have been restored, they have been repaired, they have been moved from one climate to the other one, from one concert hall to the other one. So very different history. It's like having an old-timer in a garage that has never been driven and an old-timer in the garage that has been driven for 50 years or 100 years. And obviously there's a difference in terms of repairs and stuff, so what you can see. Now here's the distribution of relaxation time that you can measure inside the back of a violin. And across that you see two peaks. And one peak can be assigned to amorphous cellulose and the other one to bound water. When you integrate the peaks, you get the amount of protons, hydrogen atoms, in bound cellulose in the cellulose and in the bound water. And so you measure a depth profile, and then you see these two peaks, the left one and the right one. And they nicely go from the front to the back over, 2.5 millimeters. And so this is a very nice back of a violin, nothing remarkable to see. Now here are the profiles of the violins at Oxford, all of them of similar quality, not here's something that could be discussed. Now, you can also measure, take the ratio and the sum of the two peak integrals. And when you take the ratio, you get a relaxation contrast and you see if there had been a surface treatment. And obviously here, the Ruggieri 1696 had a surface treatment. This one, Stradivari 1683, and that Stradivari here that had Amati had a surface treatment. And when we go to the ones in Cremona to the violins, we find that there are surface treatments also on the inside, which hasn't been known, that they're probably treated when the violin was taken apart for repair and then reassembled. And we see that these depth profiles in terms of distribution of relaxation times, they look horrible. They're not nice and straight. I mean, this looks sort of reasonable here, but this looks disgraceful. And that is sort of the sign of age. These are the wrinkles of a person in the face when they get older. These are the wrinkles of the violin. And it gives you the record of how has the wood structure changed. We had a difficult time to publish that because there are lots of experts on violins that refuse to accept that. It's a kind of statistical analysis or comparison between one set of violins and another set of violins, well preserved and with a colorful history. And but it's, I think, worthwhile pursuing that and figuring out, what changes in the would give rise to what signature in terms of the relaxation time profiles. Okay, I have to stop. And I'm nearly at the end. I stopped with paintings. You can do depth profiles through paintings. On wood, you see the signature of a paint layer, of the preparation layer, of a textile layer of the wood. It's kind of interesting. It's not really exciting because it's stuff that probably can be seen by other methods. There are some peculiarities which one can discuss. The really exciting stuff is when you look at a painting that has been restored and one that has not been treated. And you do the depth profile through the paint layer. This is, roughly 0.7 millimeters from the left to the right. And the clean painting and the NMR relaxation time, we see that as a function of depth through the paint layer, and that's straight. And NMR relaxation time is low. And here in the original, this is noisy. In the original, it's low at the surface and higher deeper down. Why is that? We discussed plasticizer loss earlier on in PVC. This is the loss, the binder is a mixture of small and large molecules. The small ones can evaporate over time. And we're just discussing 400 years of time here for the molecules to diffuse to the surface and leave. So, and the plasticizer loss means brittle material, low T2 or NMR relaxation times. And higher relaxation times means more plasticizer, more smaller molecules inside. Cleaning a painting with solvent removes the small molecules from the paint layer, makes it look beautiful, destroys the mechanical properties. And this is why one has to optimize the cleaning, the solvent cleaning process, and find the right solvent, the right cleaning method, sponge or gel cleaning method. There's another slide. I will skip it. We have studied that. And I think these are sort of the exciting perspectives of, many other things we have tried, figure out if there are forgeries, we can identify them. I haven't talked about it because they are entertaining, but not so useful. If you want to read a little bit more about the technique, I've a number of different references here. The blue ones are probably the key ones. There's a book chapter in the book by Bastidas, Springer 2018. And there is a book that is sort of geared towards the cultural heritage community. And there's a book on NMR, compact NMR, how sort of to do the measurements. If you decide, well, this is so cool, I want to try it, that might give you a little bit of help how to get started. Here is, again, some pictures of what these books look like. I want to acknowledge my former students. They're all Argentinians, all foreigners in Germany. And they decided when they left the group, they started a company, Magritech, and they sell the NMR mouse, they sell these tabletop spectrometers, and they all have been trained over 20, in these 20 years that I had the privilege to work in the cultural heritage community, and much of their education and these inventions resulted from working with the NMR mouse and measuring cultural heritage. Thank you. So here I finish with the last slide.
Yeah, thank you for that very clear presentation on a very powerful technique. So I do hope I get to use it one day. But now I want to give the audience a minute just to think and write in their question to the Q&A function. And I would like to announce and invite you to join us at our next lecture titled Dendrochronology, Tree Rings, Art Archaeology. It will be given by Pascal Fratour and Vincent Labas. So please join us on the 28th of March.